All right, good deal. So we're going to consider beams with symmetric cross-section. So when it says symmetric beam in the title, it's referring to just the cross-section, not necessarily the loading or the supports. I'll clarify that. All right, and so for the initial setup, we are going to consider a cantilever beam where X is measured along the length of the axis as usual from the fixed end to the free end. So with an applied load P that's acting at an angle from the transverse direction. All right, so far we've been mainly considering beams with transverse loads, but now what happens if that is off from that line? Now we have a horizontal component and a vertical component of that force. So I'm going to sketch all right, so we have a vertical component that is going to be P times cosine of the angle theta, and if we define theta as being the angle that it's off from the transverse direction, and then the horizontal component will be along the z-axis, P sine theta. All right, so we have P is skewed by theta from vertical, and that's in the YZ plane, right, which is your cross-section plane. So at any point along the length of the beam, in other words, at any station X, the horizontal component, I'll just write P sine or P cosine theta. Horizontal component is P sine theta, right? P sine theta will cause a moment about the y-axis. And for the cantilever configuration, the moment arm will be L minus X. And that's it, since we have the free end, right? So the moment at any point along the length about the y-axis will be P sine theta times L minus X. And the vertical component, which is P cosine theta, causes a moment about Z. And these represent magnitudes. We'll talk about direction in a moment, but I'll make a note here. So if we now consider our symmetric cross-section in the YZ plane, if we think about any point Q that exists in the positive Y and positive Z directions, or the positive YZ quadrant, then we can determine the stress at that positive y, positive z direction based on the direction of the moments and whether they will cause tension or compression. So considering the direction shown, right, for this applied skewed load, the normal stress in the positive quadrant would be negative my times the variable distance z, or the coordinate to q, divided by iy. So that's because the moment y causes compression, or the moment about y, I should say, causes compression in the positive q quadrant. And then from the moment about z, we would have, from this skewed load, the moment about z would cause tension. So it would be plus mz times y divided by iz. So I'll sketch on here the directions of the moments. Right? The moment about z caused by this load would be in that direction, causing tension at q. And then the moment about y would be in this direction, causing compression at q. Forgot to label the my there. All right, and then we'll note that z and y are the coordinates of q. So that was developed using the right-hand rule and intuiting whether you've got tension or compression at q. In general, if you just wanted to kind of enter the problem blindly and plug values in with signs associated with them, then we would have a generic equation, negative my times z divided by I minus mz times y divided by I. And this is being consistent with assuming that a positive moment would create compression in the positive direction. So that would be let's see, the sign convention would be for positive mz with the double arrows to the left, and positive my with the double arrows down.
I think double arrows work here.
So if you, it's the moment, okay, so that for MZ, we'll do that one. So the moment about Z is going to be from the load that we looked at. That was from P cosine theta in the direction that P cosine theta is down, and then you wrap your fingers around and your thumb points in the direction of the double arrows for the right-hand rule.
Okay.
Yeah. And then so for My, we had the horizontal component in the positive Z direction, wrapping around the Y-axis, our thumbs pointing down for the double arrows. Yeah. Questions?
MZ causing compression or tension at Q then? If it's here?
So because,
Are they-
right, okay, so then continuing on with that thought, right, so positives, or we have negative MZ, right? Negative MZ is causing tension at Q. Yeah,
I see it.
right, because your fingers are then
Yeah.
coming out of the page
Sure.
at Q.
Yep.
Yeah, so that would be tension going into the page would indicate compression.
So if your fingers are like going into the page at Q, then it's compression?
Yes.
Yeah, like for MY.
Okay.
Yeah. Yeah. So yeah, I honestly, like, I think this is a little bit more complicated to wrap your head around. I think it's just a lot more intuitive to look at the loads that are applied and, you know, use your right hand rule and be like, oh, or your intuition and say, okay, I can tell that it's gonna be tension here, compression there from that component. But, you know, if you prefer plugging values in and keeping track of, right, is your moment positive or negative, and then is your Z, Y position positive, negative, and this should give you the correct result. All right, so the fun thing with skewed loads is that the neutral axis is also going to be skewed, but not by the same angle as the load. So, or not necessarily, I should say, by the same angle as the load. All right, so we need to identify the orientation of the neutral axis. And we know that the neutral axis is defined as the location or the line through the cross section where the normal stress is equal to 0. So using that information, we can derive a formula to be able to apply this to any general problem, right? So if we have a cross section, we know one point on that line already, right? The neutral axis will always pass through the centroid of the section. So the first point that we know is going to be 0, 0. And so we want to find the slope of the line. All right, so we'll choose an arbitrary point in the positive YZ quadrant. All right, say the neutral axis, or we're just defining a general YZ point, which the neutral axis will pass through, right? And we're going to solve for that slope. All right, so with the criteria that normal stress is equal to 0, if we go back to our equation here, all right, so we'll do it for the example given with the skewed load like that, in that direction there. We have MYZ over IY will be equal in magnitude to MZY over IZ. So we can rearrange to solve for the slope y over z, and that will be equal to IZ over IY times MY over MZ. And then if we plug in our definitions for MY and MZ in terms of P and theta, that becomes IZ over IY times P sine theta times the moment arm divided by P cosine theta times the moment arm. And then with the P's and the moment arms canceling, we're left with y over z is equal to IZ over IY times the tangent of theta. And remember, theta is the angle by which the load is skewed. It's not necessarily the angle by which the neutral axis is skewed. So now that we've defined that slope, if we, at this point, it'll be convenient to define the angle from the z-axis by which the neutral axis is skewed. So we'll call that beta. All right, so we'll say if the tangent of beta is equal to y over z, then we can say the tangent of beta is equal to iz over iy times the tangent of theta. All right, and that we can then replace with iz over iy times my over mz, right? Just using this above that we started with before we got to this, right? Because I'm just going backwards a bit. So you can use either form, whichever one is more convenient. And then beta, defined above, but I'll write it out, is the angle from z-axis to the neutral axis. All right, so what this means is if iz and iy are the same, and that would represent, well, one example would be a square cross-section. Do you need to see more at the top, or?
Your last equation, isn't that supposed to be an I?
Is that an IY?
Yeah, I wrote a T. Thank you. Yeah, good catch. All right. So if iz and iy are the same, an example of that would be a square cross-section, then the neutral axis would be perpendicular to the applied skewed load. All right, so the skew would be the same, just with respect to different axes.
Is that like also apply to like pipes? Particular pipes?
Yeah, right. Anytime that iz and iy are the same. So, yeah, pipes, tubes with the same dimensions on both directions, things like that. All right, so then if iz is greater than iy, which is a common configuration for beams, then beta is greater than theta, and then it follows, of course, the converse. If iz is less than iy, then beta is less than theta. The takeaway there is that the neutral axis is not perpendicular to P. In all cases, All right, the points that are farthest from the neutral axis will have the largest normal stresses from bending. So for this example, the largest compressive stress would be at the point in the cross-section that is on the compression side of the neutral axis, which is the lower left side. So that would be point E. And then point B would be the location of the largest tensile stress, right? So I'll note here, this side of the neutral axis will experience tension, and this side will experience compression. So if we wanted to calculate that bending stress, we would just go back to our formula from before, negative my, and then our z distance would be positive direction for point E, value of b over 2, divided by iy. And then we would add to that our mz value. And for point E, we're going in the negative y direction from the centroid, so that would be negative h over 2 for the y coordinate, divided by iz. Right, and we would expect, since it's symmetric, point B would have the same magnitude of stress, but in tension. Any questions? Okay. So this lecture is a little bit shorter than most. We just have an example that we'll go through kind of quickly, and then since we'll finish early and since we're a little bit behind schedule, I think I'm going to go ahead and start the next lecture because that one's a little bit longer than most, so it'll even out. And then probably based on that, probably what I'll do is the recording will be on the following topic, which is shear center. So, yeah. All right, so example on the next page, we have a shape that's called S24 by 80. So it's approximately 24 inches deep. According to my sketch, it's exactly 24 inches deep. And then we have a cantilever configuration with a length of 12 feet and an applied load P at the free end of 10,000 pounds. Given the cross-section properties here, and we're going to kind of investigate the impact that just a slight skew will have on this particular cross-section. So this is an example of a shape that has a moment of inertia about z that's much larger than the moment of inertia about y. So it's much stronger in bending about z compared to y. And, again, this is a common condition for beam sections, right? Because we anticipate transverse loads on beams, and so we orient them intentionally for strong axis bending, right? But what happens if the load that you anticipate as being perfectly aligned with the vertical is slightly off skew? How could that impact the result? Well, this will give us some insight to that. So I'm going to note here IZ is significantly larger than IY. So first we'll calculate the normal stress, the maximum normal stress in the section, assuming that the load is perfectly aligned with the vertical for strong axis bending. So in that scenario, the maximum moment about Z would occur at the fixed support. So it would be 10,000 pounds times a length of 144 inches, or 1.4 million pound inches. And that's at x equals 0. So the maximum normal stress will be at the fixed end in one of the extreme fibers, right? So since it's symmetric, it doesn't matter which fiber we select. So we'll see tension and compression of the same magnitude in the cross section. So that'll be plus or minus mz times y over iz, which will be plus or minus 144 times 10 to the 4th pound inches times, let's see, since the depth is 24 inches, that maximum distance y to the extreme fiber will be 12 inches. And then we're given IZ of 2,100 inches to the 4th. So that gives us plus or minus 8,230 PSI. All right. So far, so good. So now we'll consider what happens if that load is skewed by just 1 degree from the vertical. So before we dive into this, I just kind of want to get a poll. I always do this. How far off do you think the stress will be? How much of a change? Increase, decrease, percentage? Just throw out a guess. Don't think too hard.
33%.
33%. Okay, 33%. Anyone else?
20%.
20%? Okay.
Is this like a 20% increase or?
Decrease in capacity.
No, in stress.
Oh, in
yeah,
stress.
we're not worried about capacity.
Increase in stress.
Yeah.
Yeah.
Increase in stress. Yeah. Right. Yeah, I mean, I would expect it to increase for
How
sure.
many degrees?
1 degree.
1 degree.
200%.
200%. All right. We got 20, 33, and 200. All right, a wide
Well,
range.
it should be 40 and then you just,
You got 40?
we all do 40.
All right. All right. That's good. That's enough good guesses. So we've got, first we'll gotta identify the orientation of the neutral axis, right? So go to that relationship between beta and theta. So tangent of beta is equal to IZ over IY times tangent of theta. So that's going to be 2,100 over 42.2 times tangent of 1 degree. So beta is 41 degrees. So that means we can sketch our neutral axis on here. It's going to be something like this. All right, so that's the axis about which the section will bend, if you can imagine that.
200%.
I agree.
And we already established that the maximum moment will occur at the fixed support. And so now we need to calculate our MZ and MY components. So MZ will be P cosine theta times the total length L for the moment at the fixed end. So that is 10,000 pounds times cosine of 1 degree times 144 inches. All right, which rounding, right, it's pretty much no change in magnitude for the moment from before, about Z, that is. All right, so it'll be very, very slightly less than that, but for all practical purposes, it's the same. The moment about Y, however, will not be insignificant. P sine theta times L. I'm not gonna repeat all that. I'll just put the number out there. So that's gonna be 25,100 pound inches. All right, so not only do we have basically the same moment about Z causing that stress, we have a decent moment about Y now as well that will add to stress on the cross section. So we can calculate the normal stress at point B, which is one of the farthest points from the neutral axis, right? And that will be where we see tension in the cross section. So stress at B will be, start with MY, so negative 25,100 times half of the width, which is, and we're going in the negative Z direction to get to B, so negative 7.245 over 2 divided by our IY, which is 42.2. And then plus 1.4 million, 1.44 million pound inches times the vertical distance to point B, which is positive 12, divided by 2100. So that gives us 10,400 PSI, which is right around 20%. So Bryce is the winner. And then, of course, the normal stress at E will be the compressive direction of the same magnitude.
Why is that L? Is this because we're just looking at it after reaction?
Yeah, because that's where the maximum moment will occur for this configuration. Yeah.
So then would the stress at A and D also be equal and opposite?
Yeah, I would expect them to, yeah, absolutely, because it's symmetric. So the directions will be the same magnitudes as what we calculated here, but these will be counteracting each other respectively. So it'll be a lower magnitude, but they'll have the same magnitudes at A and D. Yeah. Yes.
So like with Cash's question, L being where the placement of the load where you're gonna have the maximum moment?
No, it's the moment arm. So
Yeah.
yeah.
Right, okay.
Yeah.
But, and then the maximum moment interior to the cross-section, that's actually gonna occur where it's fixed, like at the fixed connection?
Yes, for this configuration and loading,
Okay,
right?
yeah.
A cantilever beam with a point load at the free end. Maximum moment will be at the fixed support.
Okay.
Yeah. Yeah, so if you had a more complicated loading scenario or a different configuration, right? Like if it was a simply supported beam, your maximum moment would be at the center span, right? So at L/2. And you'd have a different equation. You'd have a different equation for calculating M,
Yeah.
right? So yeah, so sometimes it would be necessary to maybe draw the shear and moment diagrams, identify where your maximum moment is, and so on.
So then X would just be the distance along the beam that you're evaluating, like in our previous, like,
Oh,
general terms.
You mean where I say x equals 0 here?
Yeah, like when we do like the
L
L
minus
minus X portion of the moment.
Oh, yeah, for this general expression. Yeah, so that was again, specific to this configuration, but we always take x as being measured positive from 0 at the left end, yeah. Yeah,
And then I got one more question on
Sure.
this one. In steel, we had a W section roof purlin.
Yeah.
On a 30% or 30-degree slope
yeah,
with a gravity load straight down.
okay,
And our strategy to calc the capacity, it was like find the max load or something like that, or size the purlin.
okay,
And our strategy was to break that load into X and Y components, or
sure.
perpendicular to the strong and
Transverse, yeah,
weak axis.
Oh, okay, gotcha.
Is that equivalent to what we're doing here?
Yeah, it sounds like it, based on what you just described. Yeah, so you're saying you had a purlin, a roof purlin that's
Mm-hmm.
at an angle, so maybe something like that,
Right,
And a load like that.
right,
And so you're saying you broke that load
Yep.
down
Right.
like that? Yep, that's essentially what we're doing here.
okay, except here we're just evaluating the stresses as it bends at, at that neutral axis, like at the extreme.
Yeah,
points.
right, we're focusing on the bending stress,
Okay.
and the effects that this has on the stresses, so, yeah. Yeah,
Okay.
so you were doing this in steel, and then you were sizing the beam based on that? So you
Right.
probably did calculate the moments, right,
Mhm.
about each axis, and then you went through that process using the steel manual
Yep.
to select a size based on that with the respective axes considered.
Right,
Yeah, so we're doing the same,
Except
Same
we're
analysis,
finding
just-
the internal stresses.
yeah, just looking at stresses.
okay.
Yeah. Yep.
It's very interesting, because doing the method in steel, if it was a 1%
Mm-hmm,
difference, you wouldn't think it's gonna cause
Oh.
a huge difference in stress, but
sure.
here it really
Yeah, it emphasizes
emphasizes
that
it, yeah.
impact for sure. Yeah, just a slight skew can cause such a big change in the stress. It is interesting.
Okay, but both
Yeah.
methods, in the future, both methods are correct for design.
Yeah,
This is essentially just like, is this just combining, but like the MYZ over IY is for like one axis, and the MZY over IZ is for the other section?
That's
just
correct.
Combining it, right?
yeah, you're just combining those effects to get the net stress, the net normal stress from
At a
bending.
specific point on the cross section.
Yes, at a specific point on the cross section. Exactly. Yeah, so you could take this approach and, if you're doing allowable stress design, then you would want to calculate the stresses. But we don't usually do that with steel,
Mhm.
so,
Right.
yeah,
Yeah.
yeah. Good deal.
Okay, cool.
Yeah.
Thanks.
No problem. Any other questions? All right. Well, I changed my mind about starting the next lecture because I think it would be kind of annoying to go 10 minutes into it and then have to pick up and recap next Wednesday. So if you guys are cool with this, it might just mean a slightly longer recording to watch to take care of that, and then yeah. All right, and then we'll start the next lecture on Wednesday. All right. Good deal. All right, well, have a great weekend. Yes.